Good afternoon, and thank you all for coming to my presentation. On behalf of my co-authors, I'm going to talk to you today about the ephemeral forests of southern Costa Rica. Here's a secondary tropical forest in southeastern Brazil. This is the Floresta da Tijuca. It's 32 square kilometers, and it's about 150 years old. In the early 1860s, these hills around Rio de Janeiro were covered with coffee and sugarcane, but they were reforested by Manuel Archer Gomez, partially through planting and partially through natural regeneration. This forest is still there today. But here's another restored forest. This is a 1-hectare experimental restoration on a cattle pasture in southern Costa Rica. This was established in 2005. Again, some areas were planted and other areas were allowed to regenerate naturally. But after 7 years, the trees were growing poorly, and the landowner ended the experiment by spraying herbicide across the entire plantation. So both of these secondary forests started out as degraded agricultural land, but one of them persisted for 140 years longer than the other one and is still going. Now, the question that my group is investigating is, why do some secondary forests persist for centuries while others are rapidly converted to alternative land uses? And the reason that this is important is because the age of a secondary forest is the best predictor of its biodiversity, structure, function, and ecosystem services. In tropical forests, for example, it takes decades to recover the woody plant diversity that you would find in an old-growth forest, and that's in good situations with plenty of propagule sources nearby. It can take much longer, centuries even, to recover old-growth-like canopy trees and vascular epiphyte communities. We've thought of at least 3 different ways to address this question empirically. First, we can track secondary forests through time. This is difficult because we only live for so long, and tropical secondary forests mature over decades and centuries. We tried this approach using a set of comparable restored forests in southern Costa Rica for which we had good data, and what we found is that there was about 33% attrition of secondary forest plots over time. Most plots were reconverted for agriculture by Costa Rican landowners. A second approach is we can survey land managers. Theoretically, land managers have all seen secondary forests created and destroyed, and through a carefully worded survey, we might be able to extract a large sample about how long secondary forests persist. We've tried this, but so far to no avail. Possibly this is because land managers don't always want to talk about projects that went awry, or maybe land managers just don't have time for surveys. A third approach, and the one that I'm going to talk about this afternoon, is using historical imagery to track forests over time. The benefit of this approach is that we can look at much larger spatial scales, but the downside is that we have more limited data about the individual forests that we're studying. They're basically just regenerating forests that appear on the landscape at some point in time and whose fates we can track. The particular landscape that I want to talk about is the Coto Bruce region of southern Costa Rica. This is an area encompassing about 500 square kilometers along the Panama border. It's pre-montane, with elevations from about 700 to 1,600 meters elevation, and it's wet. It gets 3 or 4 meters of rain per year. This is a rural area with a population of roughly 40,000 people, most of whom farm either coffee or cattle or vegetables for export. The oldest forests in Coto Bruce are approaching 500 years old. Prior to that, there's charcoal and corn pollen in lake sediments, which indicates shifting cultivation by the Ngabe people who lived here before. In contrast, European settlement was rather recent. Most of the older forests in this area were cleared for coffee plantations in 1960 through 1980. Many of these farms were subsequently converted to cattle pasture after the coffee crisis in 1989. And this is what that deforestation looked like from above. In these hand-digitized aerial and satellite images, dark gray represents forest cover and light gray represents non-forest. Coffee plantations and very early successional vegetation are classified as non-forest here. So obviously the big story is that there was massive deforestation in the middle of the 20th century, but if you focus in on the light gray areas, you can see that some of them turn back on and become secondary forest at some point. And by tracking those particular patches over time, you can see how long secondary forests persist and under what circumstances. For example, if you have a patch of forest that is deforested in 1947 but is reforested or turns on by 1960 and then remains forested until 1997, then is cleared again in 2014, you can surmise that the reforestation event occurred in 1947 through 1960 and the deforestation event occurred in 1997 through 2014. So the observed longevity of this forest patch would be 54 years, but given the infrequency of observations, the range of possible ages runs from 37 to 67 years. In this analysis, we defined a patch as a set of adjacent pixels that shared a common deforestation and reforestation history, and we only used patches that were more than a 1/10 hectare in size. All of the patches in this study were manually checked to be sure that they were properly classified. In the end, our sample included 1,750 patches of secondary forest, which ranged in size from a 1/10 hectare up to 29 hectares, and in total represented an area of 17 kilometers squared. To analyze these data, we used a survival analysis, which is a way of estimating the time until an event. Usually, that event is death in medical research. In this case, the event was deforestation. On the x-axis, we have time since the forest patch was first observed, and on the y-axis, we have the number of forest patches persisting, or the percent persisting. What we found was a precipitous decline in secondary forest persistence over the 67-year time period. 50% of secondary forest patches were re-cleared within 20 years, 78% were re-cleared within 37 years, and 85% were re-cleared within 54 years of when they were first observed. Interestingly, there was no difference in persistence between forests that appeared at different times or at different decades during this period. So contemporary secondary forests are not necessarily persisting any better than secondary forests that appeared in the mid-20th century. The short duration of these secondary forests is surprising and I think alarming, but the main question that we had was what explains the variance in forest persistence? Why do some secondary forests last longer than others? In a previous paper, we conceptualized the causes of variation in secondary forest persistence as falling into 3 broad categories: stakeholders, environment, and governance. Or put another way, what do people want from the land? What can the land provide? And what rules govern this relationship? Here we tested 6 specific predictors. We tested distance to roads, distance to rivers, distance to protected areas, elevation, terrain ruggedness, and patch size. And out of these, I'm only going to have time to show the couple that were the most significant. So the most important factor was whether a secondary forest was located near a river. Riparian secondary forests were significantly less likely to be deforested compared to other secondary forests. Here I'm showing this as a hazard function derived from Cox proportional hazards modeling. And what it shows is that the proportional risk that a given forest will be re-cleared based on distance to the nearest river. You can see that deforestation hazard increases. It's greatest for forests that are far away from rivers, such that even 200 meters from the nearest river, deforestation hazard was 50% greater than for forests immediately adjacent to rivers. This could be due to a few things. It could be due to the Costa Rican forest law, which mandates a buffer around waterways. It could also represent the fact that lands near rivers become marginal for agriculture when they're cleared and eroded into steep riverbanks. And it could be related to landowners leaving forest or restoring forest in order to protect water sources. Another important factor is that secondary forests persisted longer when they were larger in size. For example, a forest patch that was 14 hectares in size had only half the chance of being deforested at any given time compared to a forest that was only a 1/10 hectare in size. And this suggests that smaller patches of forest turn over faster than larger ones. Some of the other factors that we looked at, like elevation and terrain ruggedness, turned out to be less important here, but could be important in a larger study area. Based on these observations, we conclude that in southern Costa Rica, secondary forests are not persisting for very long. In fact, some of them could probably be considered ephemeral. We also conclude that which forests persist for longer periods of time is to some extent predictable based on their geography. As you can imagine, these results have important implications for biodiversity conservation, climate change mitigation, and large-scale forest restoration. First, the bad news. Average secondary forest longevity was much shorter than what's required to achieve old-growth levels of biodiversity or ecosystem functioning. For example, we know that it takes more than 100 years to recover old-growth levels of vascular epiphyte species richness, but most forests in this study persisted for only 20 years, and very few persisted for 50 years. Some attributes of old-growth forests recover even more quickly than epiphytes, such as tree species composition in some highly resilient forests, but other attributes take even longer, such as canopy tree architecture. As for carbon storage, here's a diagram of the potential carbon storage that could occur in Latin America by 2048, and these values are in petagrams. The amount of carbon that's stored in Latin America will depend on two factors: the amount of land that's allowed to regenerate and the amount of regenerating land that persists for 40 years. So if all regenerating forests persist for 40 years, then they'll soak up somewhere between 8.5 and 10.5 petagrams of carbon. But if forests are like southern Costa Rica, it could be less than 1 petagram, and there's potential for net carbon loss if secondary forest clearance outpaces forest regeneration. A key question here is how general our observations are. Are most secondary forests ephemeral, or is Costa Rica a special case? Our analysis indicates that approximately 2 to 3% of secondary forest patches were cleared each year between 1947 and 2014. This rate is at the lower end of other estimates from northeast Costa Rica, where annual secondary forest loss may range from about 3 to 10%, or eastern Peru, where annual secondary forest loss ranged from 3 to 23%. And I really wish that I were in Kuching today so I could find out about Naomi Schwartz's new analysis. But from the studies that I've seen so far, southern Costa Rica may be a special case. But if it is, it's an optimistic case. And that's not good news, given that 85% of secondary forest patches were cleared in 54 years. Our second conclusion is more positive, which is that it's promising that some secondary forest patches persist longer than others and that the variance is somewhat predictable. In our study, secondary forests persisted for longer periods of time when they were larger and located close to rivers, suggesting that large riparian forests could be prioritized for conservation and restoration, which is something that I think is already happening with riparian buffer rules in several countries, including Costa Rica. With a bigger study area, I think that more geographic predictors will come out, and I expect that in general, the places where secondary forests are going to persist will be similar to the places where old-growth forests persist today. That is, places that are far from people, unsuitable for agriculture, and protected from deforestation by law. One surprise for me in this study was that there was no difference in persistence between secondary forests that recovered in the mid-20th century and forests that recovered in the 1980s and 1990s. There were several major cultural and policy changes during this time that I would have expected to increase forest persistence, and the lack of a difference is a bad sign, I think, because it suggests that historical trends that I've shown here may be a good indicator of the fates of contemporary secondary forests today. So collectively, our results raise two important questions for large-scale forest restoration. First, should new tree cover be detected by remote sensing count towards national restoration commitments? I think this is going to be a temptation. For example, Costa Rica has committed to restore 1 million hectares of forest by 2020 for the Bond Challenge and New York Declaration on Forests. And Costa Rica has also experienced significant reforestation at the national scale over the last 2 decades. For instance, between 2000 and 2010, woody vegetation cover in Costa Rica increased by more than 160,000 hectares, which is roughly 16% of Costa Rica's national target met if they just counted these new forests. But if our results are general to Costa Rica, we can expect that by 2030, only about 81,000 hectares of this new forest would remain, and all but about 24,000 hectares would be re-cleared by about 2060. Second, and relatedly, I wonder if more forward-looking countries could set more ambitious restoration targets. Our data show that how long regenerating forests last is not totally stochastic. If we can predict the conditions that favor forest persistence, we should also be able to manipulate them. The forest landscape restoration movement already does this to some extent by encouraging reforestation in riparian areas and on the highest, steepest parts of the landscape. But at a national level, I think it would be really inspiring to see a commitment not to restore 1 million hectares of 0-year-old forest by 2020, but to restore 1 million hectares of 100-year-old forest by 2120. I want to thank the National Science Foundation, Missouri Botanical Garden, and the Partners Research Coordination Network. And if you'd like to learn more about this work or any of my other work, please visit my blog, The Natural History of Ecological Restoration. Now, if you have any questions, comments, or verbal abuse, you'll have to send me an email, or if he's in the room, you can ask my colleague, Zach Zahawi. Thank you for your attention.